So before, we have found that by taking the formula for the energy of the system, let's see here, at the beginning of chapter 3, we found temperature by letting the system exchange energy between two parts, and we wind up finding what temperature is when it reaches a thermal equilibrium. Here, we're going to allow the system to exchange not just energy, but also volume. So if my isolated system has two parts, A and B, with a dividing wall between them, like a piston and cylinder, which can slide freely left or right, and they can exchange energy left or right. Okay, so we have the energy, part A. Let me get rid of this little warning. The volume of A, and of course the entropy of A. Same thing for B. Okay. So just like the thermal, when we allow them to exchange energy, the exchange of energy is governed by the temperatures. Like the book notes, the spontaneous exchange of energy is governed by the temperatures. So when they reach equilibrium through the exchange of energy, it is a thermal equilibrium and they're at the same temperature. Here, when we allow them to exchange volume, which again is an odd way of saying we allow this divider to slide back and forth. But look, if one of them gains volume, the other one loses it, so really it's an exchange of a fixed volume. Then that exchange of volume is governed by their pressures, and they will come to a mechanical equilibrium when they're at the same pressure. So we'll divide that, or we'll derive that. Okay. If we look at the entropy plotted versus energy of A and the volume of A, total entropy, S total, is a two-dimensional graph here where say energy that way, volume that way. It increases to a peak in the middle versus energy. It also increases to a peak in the middle versus volume. And so the whole shape here would be kind of hard to do by hand. Like that there, sort of like a pup tent. Okay, anyway, it peaks somewhere in the middle, and somewhere in the middle range of volume of A, and somewhere in the middle range for energy of A, where the maximum is for A to have everything of both, and the minimum is for A to have nothing of either one. Okay, so when it reaches the maximum entropy, of course, the slopes versus energy and the slope versus volume are zero. So at maximum total entropy, the derivative of total entropy with respect to energy of A is zero. And the derivative of total entropy with respect to the volume of A is zero. so we've already done that one there. That got us thermal equilibrium. Now we're going to take account of the exchange of volume. So put in 0 equals ds by dVA V is VA plus VB. So dVA, well, let's see, dV is dVA plus dVB. We take a differential. If the total volume does not change, that's fixed in the problem here, then dV is 0. There's no change in it, which means dVA is negative dVB. Okay. Let's see here. Also, S total is SA plus SB, so we can expand this. All right, and oops, I made a mistake right here. I just expanded S total into SA plus SB, so it's still going to divide by dVA in both cases. All right, but dVA is negative dVB, and it's kind of awkward to take the derivative of the entropy of B with respect to volume of A, so let's switch that around. And that's all equal to 0 because we've said that that's slope 0 at the maximum. So now let's put 1 equal to the other side, get them on opposite sides. There. Good. So at equilibrium, when the entropy as is a maximum, we found that the slopes of the entropy of one side versus its volume is the same as the slope of the entropy of the other side versus its volume. Okay. And we're holding the, this is a partial derivative, so the energy of each side is fixed and the number of particles is fixed. They can exchange energy, but this is not part of this partial derivative here. Okay. All right. Reading from the book. From experience, we know that when they're in mechanical equilibrium, their pressures must be equal. If the volume isn't changing, it's because it's being pushed equally from each side. So the pressures are equal. So the pressure must be some function of these derivatives. And he says this is actually a nice little thing here. He does a kind of a quick and dirty dimensional analysis. To figure out what function of this derivative, look at the units. Entropy has units of joules per Kelvin, energy per temperature. So we've got ds by dV. Joules per Kelvin over volume, which is in cubic meters. And that will get you, let's see, a joule is a kilogram meter squared per second squared, or a joule is a Newton meter. And so if you've got Newton meters per Kelvin divided by meters cubed, you wind up with newtons per meter squared over Kelvin, which is pascals, pressure units per Kelvin. So to get something with units of pressure, we need to multiply by temperature. Let's see here. So he proposes that pressure will be temperature times, turn this around. dV by ds by dV. With number and energy held constant. Okay. He says, should we want the derivative of S with respect to volume be large or small when the pressure is large? When this slope, ds by dV, is large, the system gains a lot of entropy. There's a large change in S by just expanding just a tiny bit. So since entropy tends to increase, the system really wants to expand. And that's what we mean when we say the pressure is large. It wants to expand very hard. So that's what how he set it up that way. He says he won't try to call this the definition of pressure, but it has the same qualities as pressure does, and is probably. He says it's good to check that this actually works. If you put it in, try to solve this for an ideal gas. Okay. If we put in the equation, the Sacro-Tetrode equation for the ideal gas, where, so we have for our entropy, now this is a monatomic ideal gas, all right? We have that expanded form on it that we had before. So S equals NK log V plus 3/2 NK log U plus K log of some complicated function of number. All right. When we put that in to take the derivative with respect to V, we wind up with that term, the derivative of this term is 0, and the derivative of the last term is 0. Boy, this chalk does not work on that board. Let's try this. That's much better chalk for us. Okay, so the second and third terms are, the derivative of those are 0 because they are constant with respect to V. dNK log V by dV. Well, the NK can be pulled out. We get an NKT. Now, derivative of log V over V, part of the natural logarithm, is just 1 over V. So the pressure is NKT over V. Sounds kind of familiar. We've just re-derived the ideal gas law. So I'm going to put a big fat check next to that, say that we confirm that, at least in this case, this proposed formula for pressure works. Now, actually deriving pressure from it, there are, I'm sure, much longer articles showing why that turns out to be right. So we've done sort of a hand-wavy kind of an explanation. But we've seen that it works in this case, and in fact, this is, well, it may not be a fundamental definition of pressure, it's a correct formula. Okay, we verified it there. Next, we're going to derive a thermodynamic identity, which is a really handy equation. Okay. So, we're going to start off to answer the question, considering a process in which you change both energy and volume by small amounts, how much does the entropy change? So, we're going to divide it into two steps. Let's say if we plot the system's energy versus its volume, then, and we start off with some energy, some initial volume, let's make it a two-step process. First, we'll change the energy, step 1, by some amount delta U, and then we'll change the volume, step 2, by some amount delta V. This way we can do just one at a time and not worry about changing both simultaneously. Okay, now we know that entropies add, well, and also changes in entropies add. So if we make two changes to the system, the total change in entropy to go from this point to the final point is the change in entropy over step 1 plus the change in entropy over step 2. Logical enough. All right. Here's the neat thing. In step 1, we changed the energy. In step 2, we changed the volume. So let's see how they changed versus energy and versus the change in volume. And we can do that, again, we're always allowed to multiply by 1. And often we can get good results if we cleverly disguise the number 1 as some ratio of something divided by the same thing. So in here, let's take delta S1 times delta U over delta U, which is 1. And we'll take delta S2 change in entropy over step 2 and multiply by delta V over delta V. Now the reason that that's helpful is if I rearrange this slightly, so it's delta S1 over delta U, times delta U. Notice that this is starting to look like a derivative or a partial derivative. Same thing over here, but with respect to V. Okay. Now, in this case, well, I actually don't need to, rather than saying in step 1, well, step 1 held the volume constant. So let me just write subscript V, volume is constant. And in step 2, the energy is constant. So I'm specifying it that way. Mathematically, this is all the same that I started off with. Now, for infinitesimal changes, for very small changes, I can turn these differences into infinitesimal changes. So now I have derivatives, and because I'm only taking derivative with respect to one thing at a time, it's a partial derivative. Make sure I've done that correctly. Yes. Okay. Now here's the really nice thing. this is all straightforward. I just took it, broken into two steps, one with respect to u, the next with respect to v, multiplied by delta u over delta u, multiplied by delta v over delta v, rearranged, turned them into derivatives. So far, it's really just been mathematics. Now I can take some physics in because I know ds by du is 1 over temperature. I should write, by the way, at this point, that this is the differential of s, an infinitesimal change of s. Now, so that's 1 over temperature, and we've just arrived that ds by dv is related to the pressure. So, let's see, pressure is T times ds by dv. Now, ds by dv then is, well, it's P over T. Okay. I've got that 1 over t in both of those terms on the right. I don't really like it. Why don't I multiply both sides by t? TdS equals du plus pdv. And you know what? I'm probably mostly interested. I mean, the thing that governs so much of the laws of nature is energy. And plus it's by itself. Why don't I just solve for du, the change in the system's energy? I may need to turn, oh, I've got enough room on the screen here. So du equals TdS minus pdv. And that is a really simple, straightforward, and incredibly useful equation called the thermodynamic identity. What's going to be especially useful about it very soon is that pdv, or negative pdv, is, in many cases, mechanical work. Or I guess it is mechanical work if we hold the pressure constant. TdS is going to get identified with the heat flow. And so this is almost, but not precisely, the first law of thermodynamics. At least we'll be able to equate it with it and to solve for interesting things. He makes a note. If you memorize only one formula from this chapter, make it this one. Because from this, you can recover most of the other stuff that we've done. If you know this, then whatever you're holding constant, make its differential be 0 and solve for everything else. Okay, so we'll stop there.